Welcome to the deep dive. Today we're getting into something pretty fascinating in cloud computing, how AWS Lambda handles, well, instantly starting and scaling serverless functions, especially now they can be these huge container images.
Exactly. And we've got a great source for this, a technical paper from Usenix ATC 23. It's straight from the AWS engineers who actually built this thing. So, it's the real deal.
Yeah, this isn't just theory, it's like looking under the hood of a system that's running millions of functions a second for what, over 1 million customers?
Mm-hmm. A massive scale.
And the core problem they solved is, well, sounds kind of impossible. You've got these potentially giant container images up to 10 gigs, right?
Yeah, huge.
And you need them to start in maybe 50 milliseconds.
Yeah.
A cold start.
Right. And not just start fast, but scale massively, like 15,000 new containers per second for just one customer, potentially.
Wow. Okay. So our mission today is to unpack how they actually did that. How did they get around this huge data bottleneck with large containers? We're going to focus on their on-demand loading system.
Yeah, we'll look at the core ideas, the clever tricks that make it all work so fast. It's pretty ingenious stuff that makes that low latency happen for you.
Okay, let's dive in. Because Lambda wasn't always like this, was it? Originally, functions were much smaller, like 250 megabyte zip files.
That's right. A really important starting point. Back then, downloading and starting was, relatively simple, faster, but people wanted to build bigger, more complex apps, more dependencies.
Yeah, you hear that a lot, needing more libraries, more tools.
Exactly. And the demand just grew and grew for supporting container images, like Docker, familiar tool.
Which creates this tension, right? Customers want the big images, the flexibility, but they absolutely can't lose that super fast Lambda cold start.
Precisely. That's the core conflict. A slow start kind of defeats the purpose of serverless for many use cases.
Totally. Imagine waiting minutes. No way.
And the paper quantifies this data problem really starkly. Think about starting 15,000 containers, each needing 10 GB.
Okay.
If you just downloaded it all, that's 150 petabytes per second of network traffic.
150 petabytes per second.
Yeah, it's an astronomical number, just completely impractical.
Okay, so brute force download. Definitely not happening. So what were the key insights, the things that let them rethink this?
Well, they looked at how people actually use these containers in Lambda, and they found three sort of simplifying factors. First was cacheability.
Catchability,
Oh.
meaning things get reused.
Exactly. Even with millions of functions, those big scale-up spikes, they're often driven by a smaller set of popular images. So huge potential for caching that common data.
Okay, that makes sense, like popular base images or common frameworks.
Which leads straight into the second factor, commonality. So many containers share the same base layers. AWS base images, Alpine Linux, that kind of thing.
Right, you see those everywhere. Docker Hub downloads are in the billions, the paper mentions.
Billions. So massive opportunity for deduplication. Don't store the same layer a million times, store it once.
Okay, cacheability and commonality, reuse, and shared foundations. What was the third?
The third one is really interesting, sparsity.
Sparsity, like sparse data.
Sort of.
Yeah.
Turns out most applications, when they start up, they don't actually need all the data in their 10 GBB container image right away. The paper cites research showing, on average, only about 6.4% of the data is touched initially.
Only 6%. Wow.
Yeah, so you don't need to move everything if you only need a tiny fraction to get started.
Right. That changes everything. Cache it, deduplicate it, and only load the bits you actually need right now.
You got it. And the core technologies they used reflect that. Caching, deduplication, erasure coding, we'll get to that, and this sparse on-demand loading.
So how did they implement this sparse loading? The paper talks about block-level loading.
Right. So instead of trying to understand the container file system directly, like some other approaches do, the paper mentions Slacker and Starlight, which work at the file level.
Okay.
AWS chose to operate at a lower level, the block level, using the Versio-Blick interface.
Why block level? What was the advantage? Security, mainly. They felt that managing lots of overlaid file systems in the shared infrastructure was too big an attack surface. By using VirtuoBulk, all the file system logic stays inside the isolated micro-VM for each function. Safer.
Ah, okay. Keep the complexity contained within the secure boundary. Makes sense. So how does this block level thing actually work? You mentioned deterministic flattening.
Yeah, that's pretty clever. When you create a function, which happens relatively infrequently, right, when you update code or config, maybe takes minutes.
Not when it runs, but when you deploy it.
Exactly. During that creation process, they take all the layers of the container image, which are basically tar balls, and overlay them into a single flat x4 file system image.
Okay, so they pre-process the layers into one file system.
Right. And the key is deterministic,
Meaning?
meaning if the files haven't changed, the resulting blocks in that flattened file system are identical every single time.
Ah, and that's crucial for deduplication later, isn't it? If the blocks are identical, you can spot the duplicates. Precisely. They even had to use a modified ext4 implementation to make sure things like timestamps or directory order didn't create differences unnecessarily. They force it to be predictable.
Wow, that's deep in the weeds. Okay, so you have this flattened, deterministic file system image. What next?
They chop it up into fixed-size chunks, 512 kilobytes each.
512K, why that size?
It's a trade-off, you know.
Yeah.
Smaller chunks might give slightly better deduplication maybe, or help random access, but larger chunks mean less metadata to track and potentially better throughput for sequential reads. 512K was likely their sweet spot based on observed workloads.
Okay, so you have these chunks. Where do they go?
Initially, they get uploaded to S3, which acts as the backing store at the origin.
Mm-hmm.
Now, when a function needs to start on a specific worker machine, the Lambda control plane tells a component on that worker, the micromanager, hey, start this function.
Gotcha.
The micromanager spins up a Firecracker micro VM that's the secure sandbox, and it creates a little helper process, a local agent, just for that function instant.
Okay, a VM and an agent per function.
And micro VM gets two virtual block devices. One is a common root file system. The other is special. It's connected to that local agent using FUSE.
FUSE file system in user space. So the agent pretends to be a disk drive.
Basically, yeah. It exposes those 512K chunks as if they were a block device to the micro VM.
Clever. So how does the code inside the VM actually read its files?
When the code tries to read something, a library, data file, whatever the request, goes to that IFUS lock device. Firecracker intercepts it, sends it to the local agent. The agent first checks its local cache right there on the worker.
The L1 cache?
Exactly. If the 512K chunk needed is there, boom, served instantly. Super fast.
And if it's not in the local L1 cache?
Then the agent goes and fetches it from the next cache tier, this shared AZ level cache we'll talk about, or ultimately from S3 if needed.
Okay. And what about writes? If the function modifies a file?
Writes go to a separate overlay, also managed by the agent. It uses copy on write at the page level. So only the change data blocks get written locally. This is super important because it keeps the cache chunks immutable.
Immutable, meaning they don't change.
Right. Which means they can be safely shared between many different running instances of the same function, or even different functions if they share base layers.
Got it. So that block level loading plus local caching tackle sparsity only load what you need. Now let's talk deduplication again. Those stats were pretty wild.
They really are. The commonality aspect pays off big time. Remember, 80% of new function uploads result in 0 unique chunks being added.
80% just blows my mind. Probably supply-city pipelines just redeploying the same thing, right?
Very likely. And even for the other 20%, the average unique data is only 4.3%, median 2.5%. Tiny fractions.
And this saves a lot of storage, the paper says.
Oh yeah, up to 23x reduction just from deduplicating identical chunks, and another 5x by getting rid of all 0 chunks during creation.
Yeah.
Massive savings.
Deduplication and encryption, they seem like opposites, don't they? Encryption tries to make everything look random. Dedupe needs identical things.
That's the core challenge they had to solve. How do you find identical data when it's all encrypted?
So how do they do it?
They used a technique called convergent encryption.
Convergent encryption.
Okay, the idea is you derive the encryption key for each chunk from the content of the chunk itself, usually using a cryptographic hash like SHA-256.
So if two chunks have the exact same content?
They'll produce the same hash, therefore the same encryption key, and therefore the same encrypted ciphertext.
That's clever. So the encrypted versions will be identical if the plaintext was identical.
Exactly, allowing them to spot and store only one copy of the identical encrypted chunk. Duplication achieved, even with encryption.
Okay, but wait. If the key comes from the content, couldn't multiple customers end up using the same key if they happen to have an identical chunk, like a common library file? How is that secure?
Great question. That's where the image manifest comes in. For each image, Lambda creates a manifest file. This manifest lists all the chunks in the image. Their offset, the unique key derived from the content, and a hash of the chunk.
Okay, a list of ingredients.
Right. And this entire manifest is then encrypted with a per customer key from AWS KMS using AES GCM.
So even if two customers have an identical chunk encrypted with the same content-derived key, they can only access it if they have their own customer-specific manifest, which is encrypted just for them.
Precisely. The manifest acts as the secure pointer to the deduplicated encrypted data. And there's a nuance. They only encrypt the key table within the manifest with the customer key.
Hmm.
The list of chunk hashes itself is just authenticated.
Why only encrypt the keys?
It helps with internal operations like garbage collection. They can see which chunks in image references without needing the customer's key to decrypt the actual chunk keys.
That's really smart, balancing security, deduplication, and operational needs. And workers verify integrity too, right?
Absolutely. When a worker downloads a chunk, it uses the info in the manifest, which it decrypts using the customer key, to verify the chunk's integrity using a message authentication code, MAC. End-to-end protection.
One thing they didn't do was plain text compression before encryption. Why skip that? Seems like it could save bandwidth.
They considered it, but decided against it for a few reasons. One, the latency overhead of decompressing every chunk might negate the bandwidth savings, especially on AWS's fast internal network. Random access also gets harder with compression. And two, there's a potential security risk compression side channels. Attackers might learn something about the plain text by observing the size of the compressed ciphertext.
Ah, right. So latency and security concerns outweighed the potential size reduction benefit. Makes sense for Lambda.
Though they do handle all zero chunks specially, which is a form of compression, really.
Now, this heavy deduplication, it introduces a potential risk the paper calls blast radius. What's that about?
Yeah, so if one specific 512K chunk becomes super popular, maybe part of a core library used by thousands of functions, any problem with that single chunk, maybe you get slow to access or corrupted or unavailable temporarily, could impact a huge number of functions. The blast affects a wide area.
Okay, a dependency bottleneck risk. How do they limit that blast radius?
They use another clever trick with the convergent encryption. Remember how the key is derived from the content hash?
Yeah.
They add a salt into that key derivation process, just an extra piece of random data.
Okay, like salting a password hash.
Exactly. And crucially, they can change this salt value based on time or maybe how popular a chunk is or even where it's being created in the infrastructure.
Ah, so if you use a different salt, even for the exact same content,
You get a different key and a different ciphertext. It won't deduplicate against chunks created with a different salt.
so they can intentionally create separate copies of very popular chunks by changing the salt, breaking the deduplication link, and limiting the blast radius if one copy has issues.
You got it. It lets them trade off dedupe efficiency versus risk, controlled entirely when the chunk is created. Very flexible.
That's neat. Okay, related to managing chunks, garbage collection, how do you safely delete unused chunks in this distributed, deduplicated system without accidentally deleting something still needed?
Yeah, GC is always tricky in these systems, especially without a central who uses what directory. The risk of deleting needed data is high.
So what's their approach?
They use a generational garbage collector based on roots. Think of a root as a collection, a namespace for manifests and chunks.
Okay, like memory generations and programming languages.
Kind of similar, yeah. New data, new manifests and chunks always goes into the current active root. Periodically, they declare the current root retired and create a new active root.
So older data is in retired roots.
Right, retired roots become read-only. And any data in a retired root that's still needed by an active function gets migrated, copied over into the new active root.
I see. So active data eventually consolidates in newer roots.
Exactly. Over time, a retired root has less and less active data reference from it.
Yeah.
Eventually, it can be marked expired.
Expired. What does that mean?
It's a safety period. The data is still there, but any attempt to read from an expired root triggers an alarm.
Ah, safety net. To catch unexpected accesses before deletion.
It allows human intervention if something's wrong with the migration or if data is still being used unexpectedly. Only after that expiry period, with no alarms, is the root actually deleted.
That sounds very robust. Multiple layers of protection against data loss, even if it means storing data a bit longer sometimes.
Definitely prioritizes safety.
Yeah.
And they mentioned including the active root ID in the deduplication salt as well.
Why do that?
It prevents new chunks in the active root from deduplicating against identical chunks that might still exist in older retired roots being garbage collected.
Yeah.
Keeps the generations cleaner.
Makes sense. Okay, so we've covered loading, dedupe, GC, now speed. The tiered caching. Let's get into that.
Right, the 3 tiers. We mentioned the L1 cache on the worker itself.
Yeah.
Super fast, closest to the CPU.
Then if it's not there.
It goes to the L2 cache. This is a shared cache within the availability zone. Bigger, shared by many workers, but still pretty fast.
In the last resort.
L3 is Amazon S3, the origin store. Durable, massive, but higher latency than the caches.
So L1 local, L2 shared in the AZ, L3 is S3. Tell me about that L2 cache. It sounds critical.
It is. It's a custom-built system, uses HTTP2 for efficiency. Internally, it's actually two-tiered itself.
Oh.
Yeah, a small, super fast in-memory tier for the really hot chunks, and a larger tier on flash storage for less hot but still cached data.
And how do they decide what stays and what goes?
They use LRUK for eviction. It's a variant of least recently used that's better at handling scans, like if a background job reads lots of cold data, it won't immediately kick out frequently used hot data.
Okay, smarter eviction. And how is data spread across the L2 cache servers?
Consistent hashing mostly.
Yeah.
Distributes the load across the cache fleet within the AZ.
And the performance gain is huge, right? L2 versus
Yeah.
S3.
Oh, massive. The paper quotes median L2 hits around 550 microseconds, fetching from S3, median 36 milliseconds. Orders of magnitude difference.
Wow. And how often do they actually hit the caches?
Their numbers are incredible. Median figures showed 67% of requests hit the L1 cache right on the worker.
2/3 locally. Nice.
Another 32% hit the L2 cache in the AZ.
Okay, so 67 plus 32, that's 99%.
Pretty much, leaving only about 0.06% of requests, on average, needing to go all the way back to S3. The caching is incredibly effective.
Less than 1 in 1,000 requests hitting S3. That's amazing.
It really shows how well they leverage locality and reuse.
But they also do something unusual for caching. Erasure coding in the L2 cache. Why?
Yeah, that's interesting. They use it similar to their separate EC cache paper for a few reasons, mostly around tail latency and resilience.
Tail latency, the slowest requests.
Right. In a simple cache, if the server holding the chunk you need is slower down, your request gets delayed significantly, or it's a miss. Replication helps, but it doubles the storage cost.
So erasure coding is a middle ground.
Sort of. They use a 4 or 5 code, meaning they take 4 data blocks, generate 5 encoded stripes, and store those 5 stripes on different L2 cache nodes.
Okay.
To reconstruct the original data, a worker only needs to successfully fetch any 4 of those 5 stripes.
So if one server is slow or down, it just gets the other 4 and rebuilds the data.
Exactly. It tolerates one failure or slow response without impacting the latency for the requesting worker. It costs 25% extra storage and request overhead, but significantly improves tail latency and resilience.
Plus, it helps with load balancing for popular objects too, I guess. Spreads the requests out.
Better resilience, better tail latency, better throughput for hot objects compared to simple caching.
But these super high hit rates, they can be risky too. The paper mentioned metastable failures.
Yeah, that's a potential issue with any system relying so heavily on caches. If something causes a big drop in the cache hit rate, maybe a huge sudden workload shift or a cache clearing event.
Then S3 suddenly gets hammered.
Exactly. The load on S3 and the rest of the system could spike massively, maybe hundreds of times the normal rate. While S3 is built to scale, that sudden shockwave could cause latency increases everywhere, making it harder for the caches to refill, potentially creating a downward spiral.
A metastable state where it's hard to recover, so how do they prevent that?
They have mitigations higher up in Lambda. Concurrency limits are key. If start times rise and too many functions are starting concurrently, Lambda will start rejecting new requests temporarily. Rate limiting, essentially.
Buys the system time to catch up.
Right. And they also proactively test cold starts from empty caches under high load, stress testing the recovery path.
Constant vigilance. Makes sense at that scale.
Yeah.
They also mentioned cache sizing using the 5-minute rule.
Yeah, balancing the cost of cache, memory flash, against the cost latency penalty of a miss, guided by principles like the 5-minute rule, but ultimately tuned to meet their specific hit rate and latency goals.
It's a whole complex optimization problem.
Definitely. Now, switching to implementation details. They used Rust for key parts, right?
Yeah, the local agent, the cache servers, cited performance instability, which you hear a lot about Rust.
And they shared that interesting story about fighting the compiler's auto-vectorization.
Right, where small code changes accidentally disabled optimizations, causing big slowdowns, especially in erasure coding.
Shows the level of performance tuning needed. They had to be really explicit in the code to guarantee the vectorization they needed.
But they liked Rust's built-in benchmarking tools for catching that stuff early.
Yeah, good tooling makes a huge difference for performance work.
And latency numbers. L2 cache GTs under 50 microseconds median. PUTs under 125 microseconds. That's fast.
Really fast server-side latency. Shows the cache itself is highly optimized.
They also showed end-to-end latency at the agent, which had that multimodal shape.
Right. You can see the bumps corresponding to L1 hits, L2 hits, and the rare S3 fetches. Makes sense, but they noted it makes performance analysis tricky. Averages can hide that detail.
And their experience with FUSE, good for starting, but hit performance limits.
Pretty much. Convenient, good security model initially, but the overhead from context switching and scheduling became a bottleneck at scale.
So they're moving away from it towards what?
User fault FE and MAP. More direct ways for the agent to handle memory and I/O for the micro VM, cutting out FUSE overhead.
A common pattern. Use simply tools first, then optimize aggressively when needed.
Exactly. USE let them build and iterate quickly early on.
The paper also situated their work relative to others, like Slacker, Starlight, highlighting the differences in their block-level approach and integrated caching dedupe.
Yeah, acknowledging related work but showing their unique contribution for Lambda's specific needs. And nodding to older dedupe systems too.
Okay, so wrapping this all up, it's genuinely impressive. Lambda's system for loading these big containers on demand, it's this intricate dance of caching, clever deduplication, using convergent encryption, erasure coding for resilience, and that unique block-level loading.
Absolutely. All orchestrated to give you that fast start and massive scale, even with 10 GV images. It's a complex beast, but incredibly effective.
And there are broader takeaways here, aren't there, for systems design in general?
Definitely. The paper touches on that tension with containers, super convenient, but potentially inefficient. Still room for lighter weight options, maybe.
And the critical role of caching, but also its dangers. Monoistable failures, tricky latency distributions, areas needing more research.
Yeah. And just reinforces how powerful micro VMs like Firecracker are becoming for isolation and virtualization. Lots of potential there.
Plus, they're not done. They mentioned ongoing work on cost, performance, snap start, moving off FUS.
It's always evolving, which is cool.
So, a final thought for you listening. Think about these ideas: on-demand loading, smart caching, deduplication. Where else could these principles apply? Other big data problems, maybe even stuff on your own computer. What other data bottlenecks could be solved with this kind of thinking?
It's a great question. Lots of ingenuity packed into solving this specific Lambda problem.
Indeed. Well, thanks for joining us for this deep dive.
See you next time.